For the first question, 2-10C, we asked to model an egg with heat transfer. I chose a spherical coordinate system and one-dimensional transient with temperature changing over time, and a coordinate system that would also be spherical. For 2-24, we had a cylindrical wire with three different R radiuses. I used an energy band, and we're asked to find the derived equation for the cylindrical balance, assuming steady state one-dimensional long cylinder and heat generation. We could use the energy balance to sub in terms, take limits, cancel out terms, and get to the equation down here, 1 over r dr that we're looking for. For question 2-66, we were asked to find the temperature variation and the heat flux inside of this module right here that was assumed to be a gray body with some other nodes up here. We started with this del equation right here, integrated it to get C1. We plugged in the boundary conditions with the heat flux and found that C1 was equal to negative Q dot over K. We plugged that in and then used another boundary condition to solve for C2 equaling T naught. And we use both of these values to get the temperature variation, as well as we were asked to find the heat flux, which is equal to the solar minus the convective and conduction terms, which gave us the heat flux absorbed for this specific container. For question 2-102, we were asked to find, we were given a resistance wire with these things right here. We find the PEs, the boundary conditions for this wire, and the temperature at the center of the wire. So using the cylindrical coordinates equation, we could derive using integration and boundary conditions to get the temperature variation to be T infinity plus E dot gen over 4K times R naught squared minus R plus E dot gen R naught over 2H. The boundary conditions were chosen so that the temperature change at the center of the wire was equal to 0, and the temperature change at R was equal to the convection forces. And using these two, we could solve for C2 and C1, plugging in for our variation. And then with that, we can find the temperature that we wanted, which using unit conversions and plugging in values, we find the temperature to be 125 degrees. For 14-29C, there is not enough time for the water vapor to phase out of the air, and most will be in the liquid phase while that is in the lake. 14-35C can use specified values to find P vapor, and it would equal the saturation of water, pressure saturation of water over the pressure to give you your known values. For 14-44, we're asked to find the concentration of water in the vapor phase as well as the mole fraction of air to H2O. Using Raoult's law and the PVAP tables with the handout, we can find the saturation for the given temperature and pressure. With that, we can find the vapor phase composition using the combined pressures. We can find the pressure in air, and as well as Henry's law, we can use both of these values to find the amount of air in the water, which is equal to this value down here.